The sun is the source of most of our energy here on Earth. Energy from the sun is used to produce electricity using photovoltaics and solar thermal plants. That same energy is also used for heating using solar domestic hot water systems, hydronic heating, solar air heating, and solar cooking, just to name a few. This video will talk about how the sun produces that energy. The sun produces energy using a process called fusion. Let's start our explanation of fusion with the atom.
Heat is transferred from your skin to the sweat on it to make it evaporate. How does that happen? Heat, or kinetic energy, is transferred from an area where it's currently high, your skin, to an area where it's lower, your sweat and the air. The heat transfer continues until equilibrium is reached, or until all the molecules in a given area have the same energy. There are three ways to transfer this energy: conduction, convection, and radiation. Conductive heat transfer is what happens in this picture. When heat is transferred along the handle of the pot, this heat is transferred between atoms in contact with each other. In a solid, molecules transfer vibrational energy physically to their bonded neighbors. Imagine linking arms with everyone in the class, so you're trapped in a solid form, and then try to transfer energy just by bouncing in place. Conduction also happens in liquids and gases. In these cases, heat or kinetic energy is transferred during collisions. Convective heat transfer is a much more efficient method of heat transfer for gases and liquids. During convection, millions of molecules of gas or liquid transport heat quickly by diffusion or currents. For example, in this image you can see that at the bottom of the pot, heat is conducted by the hot surface to the water at that hot surface. That heat makes that water expand and become less dense. That water then rises to the top of the pot, displacing the colder, denser water at the surface, which then sinks to the bottom and is heated by the conductive pot. Through this process, the heat is rapidly convected through the entire fluid in a continuous cycle. During radiation heat transfer, electromagnetic waves are released from a...
The higher the temperature, the shorter the wavelength of emitted radiation. The sun, with its high surface temperature, emits a great deal of high-energy, short-wavelength radiation. Energy emitted by the sun is also referred to as solar, or short-wave radiation. Most of solar radiation is the visible light we see with our eyes, but it also includes wavelengths that we cannot see, like the ultraviolet light that causes sunburn. The Earth, however, being much cooler than the sun, emits lower energy, longer wavelength radiation. Energy emitted by the Earth is also referred to as terrestrial, which means land-based, or long-wave radiation. Although we cannot see long-wave radiation with our eyes, we detect it as heat. In summary, the types of radiation emitted by the sun and the Earth are determined by their temperatures. The sun, which is very hot, emits high-energy, short-wave radiation, while the Earth, which is much cooler, emits lower-energy, long-wave radiation.
Once the pumps come on, the panels fill with water, and when the water reaches the top, it runs back downhill to the tank. When the pumps shut off, the water drains out of the piping and back into the tank, so there's no water left in the panels at night.
phenomenon, named after where it often occurs, greenhouses. As you probably know, greenhouses are buildings designed to grow plants. They typically have roofs or walls of glass. Glass, which is mostly made of a compound called silicon dioxide, is transparent to visible and ultraviolet light. However, it's not transparent to infrared light, which is another name for what we call heat. In a greenhouse, ultraviolet and visible light enters the building. It is absorbed by the building's contents, with some of the energy being re-emitted as lower energy infrared radiation. The infrared radiation is then trapped in the building, resulting in a slow rise in temperature. This, of course, is the same phenomena that causes the interior of a car to heat up on a sunny day when the windows are closed. The same phenomenon is happening at a global scale. We replace the greenhouse with the Earth and its atmosphere, with the atmosphere playing the role of the greenhouse glass. How effective is the atmosphere at trapping the infrared radiation? That depends on the gases in the atmosphere. The main contributors to trapping of greenhouse gases are water vapor, carbon dioxide, methane, and nitrous oxide. Their contribution to global warming depends on 1, how effective the molecule is at absorbing infrared radiation, 2, the residence time that the gas naturally has in the atmosphere, and 3, the total concentration of the gas in the atmosphere. This image shows the electromagnetic absorption spectra for these 4 primary greenhouse gases. At the top, you see the electromagnetic radiation transmitted by the atmosphere. This red region represents the incoming solar radiation, whereas the blue represents the outgoing thermal radiation. The x-axis is the wavelength of the radiation. As you can see here in the total absorption and scattering graph, water vapor and carbon dioxide contribute the most to the total absorption and scattering in the atmosphere. Methane and nitrous oxide, molecule for molecule, are 70 times more absorbent than a carbon dioxide molecule, but they're less abundant in the atmosphere than CO2. You can see in this graph that the global greenhouse gas emissions continue to rise, with energy being the largest proportion. Again, this trend is directly related to the fact that 65% of the global energy resource is fossil fuels. Recovering energy from fossil fuels results in the emission of a range of toxins to air, water, and soil, including the emission of greenhouse gases. The greenhouse gases absorb the infrared radiation re-emitted from the Earth, effectively trapping heat within the Earth's atmosphere. The primary contributors to global warming are water, carbon dioxide, methane, and nitrous oxide. Carbon dioxide is of the greatest present concern because it's a direct result of our global use of.
If we look at this mock of this wall cavity that we have here, we can see that obviously there's some different things going on here. First of all, we know that, like I said, heat can transfer right through building materials, but that air can actually pass through these electrical boxes and into that wall cavity and get air currents moving in there if that installation's. In this installation over here, they installed this energy block, which keeps that air from moving through there. And this other side here, where it's not installed properly, we've simply taken the fiberglass and smashed it in between there, compressing that fiberglass, reducing that R value for that fiberglass. It's not going to resist that heat loss as well. As we look at our rim joist, we can see some other examples of where that heat can transfer out. Like I said, heat can transfer right through building components, and when we use an infrared camera, we can really see where you can see each one of these rim joists or each one of these 2x6s or 2x4s in the wall cavity, every 16 inches on center. You can see those with an infrared camera fairly easily. But if we insulate in between, so we have, for this example, this is a 2x4 wall, so we have an R13 R value in this wall. Over here we have spray foam insulation, which is a higher insulation value. And it also, nice thing about this air seals up, it gets behind those electrical boxes, so we don't have that air transfer through there. In the rim joist, this is an example of, this is a basement wall, this is the upstairs floors, this is the rim joist area in between. We want to make sure that not only is this insulated properly, we want to make sure that it's also air sealed properly so that air doesn't get through there transferring heat, but also in this situation, it can transfer moisture and get back behind there and rot out these areas.
named after where it often occurs, greenhouses. As you probably know, greenhouses are buildings designed to grow plants. They typically have roofs or walls of glass. Glass, which is mostly made of a compound called silicon dioxide, is transparent to visible and ultraviolet light. However, it's not transparent to infrared light, which is another name for what we call heat. In a greenhouse, ultraviolet and visible light enters the building. It is absorbed by the building's contents, with some of the energy being re-emitted as lower energy infrared radiation. The infrared radiation is then trapped in the building, resulting in a slow rise in temperature. This, of course, is the same phenomena that causes the interior of a car to heat up on a sunny day when the windows are closed. This same phenomenon is happening at a global scale. We replace the greenhouse with the Earth and its atmosphere, with the atmosphere playing the role of the greenhouse glass. How effective is the atmosphere at trapping the infrared radiation? That depends on the gases in the atmosphere. The main contributors to trapping of greenhouse gases are water vapor, carbon dioxide, methane, and nitrous oxide. Their contribution to global warming depends on 1, how effective the molecule is at absorbing infrared radiation, 2, the residence time that the gas naturally has in the atmosphere, and 3, the total concentration of the gas in the atmosphere.
Have different experiences under the hot sun?
Yes, indeed. First, let's talk about the heat, since that's really what this case is all about. Now, believe it or not, heat is a form of light.
What?
Here, Mr. Savage, take this flashlight and shine it at this mirror.
I can't see.
And why not?
Because the light is reflecting back into my eyes.
That's right. Now, the important word here is reflecting. Because now, Mr. Savage, I want you to shine the light at this old piece of wood. Okay, good. Now what's happening?
I'm still having trouble seeing.
Very good, Mr. Savage. So where does the light go?
Some of it gets absorbed in the wood.
Absorbed into the wood?
That's right. The light gets absorbed right into the wood.
You mean like a sponge?
Well, yeah, I guess you could say that.
And is in the middle of explaining his experiment. Let's return to the courtroom to find out what happens.
Well, heat can be either reflected or absorbed, just like light.
I don't get it.
I'd better show a demo. Fred, could you turn on the laboratory sun lamp, please?
Okay.
Hey, the temperature's going up.
Now, do you know why?
Because the sun lamp is very hot.
Well, that's right. But look, the thermometer with the black shirt is heating up faster.
So that explains why Mr. Richmond was very hot and felt faint.
That's right.
Just because of the shirt color?
That's correct. The black absorbed a lot of the heat while the white reflected it. Do you know why a white shirt like this looks white to us?
Because it's white?
No.
How could I have missed that one?
It looks white because it is made in such a way as to reflect light and heat. The white color you see is actually reflected light and heat coming off the cloth.
But the black cloth of this shirt is not reflecting any light or heat, is it?
No, ma'am, it isn't. It's sucking the heat and light in and trapping it, getting hotter and hotter.
Thank you, Professor Parsons.